space to a vector space A. And the question is, what are the genetic fibers of such map? So this map is called Hitchin map or Hitchin fibration. Okay. And the next, using this morphism, we will prove a Torelli theorem that says if two such moduli spaces over two different curves x and x prime, if they are isomorphic, then the underlying curves are isomorphic. That x is isomorphic to x prime. Okay. So in other words, we can recover the curve from the moduli space itself. Okay. So in case of parabolic setup, we need one more condition, that this isomorphism between x and x prime should also preserve a fixed finite set. Okay. We'll see that later. Okay. Sorry. Okay. Let me define the Higgs bundles. So let X be a compact element surface of genus greater than or equal to 2. And let K be the canonical bundle, that is a cotangent bundle in case of curves. Okay. And so a Higgs bundle over the curve X is a pair E comma phi, okay, which consists of a vector bundle E and a morphism phi from E to E tensor K. So this morphism is called Higgs field. So so you can think of it as an endomorphism of E with values in K. Okay. An example, so any vector bundle is a Higgs bundle. I mean, if you consider the zero morphism here, the phi is 0 in that case. Okay, so which means that the moduli space of vector bundle sits inside the moduli space of Higgs bundle. Also, you have a sister axon on this Higgs bundle, which sends the Higgs field phi to lambda phi. Okay. And the slope stability condition says that a Higgs bundle E comma phi is stable, respectively semi-stable, if every non-zero phi invariant subbundle. So phi invariant means that phi restricted to F sends F to F tensor K. Okay, so it preserves F. For those subbundles, we have this slope inequality. Strictly less than for stability and less than equal for semi-stability. So degree of a vector bundle means degree of the determinant bundle, which is a line bundle. Okay. So since we have the notion of stability, we can say that let's consider the moduli space M of stable Higgs bundles over X of a fixed rank and fixed degree. Okay. Now the sister axon here, it has a nice property. It preserves the stable vector bundles. So if E comma phi is stable, then E comma lambda phi is also stable. So therefore, the sister axon induces a sister axon on this moduli space. Okay. And this moduli space of Higgs bundles is, I mean, it has some nice properties, like it is hyperkähler, it is irreducible, variety, and many others. But this is very interesting object to study nowadays, this moduli space. So the phi, that is Higgs field, is a morphism from E to E tensor K. So you can think of it as a an element of the endomorphism of E with values in K. So you can talk about the characteristic polynomial of phi, okay, where this coefficients Si of the characteristic polynomial, they are basically a trace of OH I phi. Okay, so for example, that S1 is a trace of phi. Okay, and SR, that is a determinant, that is a trace of top exterior power of phi. Okay. Therefore, we have a morphism H from this moduli space to a vector space A, which is the direct sum of H naught of K power I. So these A's I, they're basically elements of H naught K power I. Okay. So this map sends the Higgs field phi to the coefficients of its characteristic polynomial. So this is called the Hitchin map. So it was introduced by Hitchin in 1987. And this is one of the basic tool to study the Higgs bundle. So what are the fibers of this map? Okay, so you can consider the spectrum. So since we have the characteristic polynomial, the zeros of the characteristic polynomial is called the spectral curve, which is denoted by S. And it comes with a projection map pi from S to X. And we can consider a line bundle of degree 0 is Jacobian of S. L is a line bundle of degree 0 over S. And then the push forward map gives a Higgs field on pi star L. Okay. Therefore, the push forward of L together with that canonical map is a Higgs bundle. So what we have seen, this is the loop. If we begin with the Higgs bundle, then consider the characteristic polynomial of the Higgs field. And then the zeros of that characteristic polynomial gives you the spectral curve. And then if you consider line bundle over that spectral curve, the Jacobian. And then the push forward, this gives you a Higgs bundle. Okay? This is a loop. So for the moduli space of Higgs bundles, this generic fibers of this map H, they're basically Jacobian of S. Okay. So in particular, they are abelian varieties. Okay. Okay, let me introduce the parabolic bundles. Let D be a fixed finite set P1 to Pn of n distinct points. The parabolic bundle is basically a vector bundle together with a weighted flag over each point of D. Okay. So formal definition, the parabolic bundle is a vector bundle together with a parabolic structure over D. So we fix this D throughout this top. Okay. So parabolic bundle is over D. So parabolic structure over D means we have a filtration of subspaces. So this EP is the fiber space, fiber of over P. Okay, so it has a filtration of subspaces, and there is a sequence of real numbers which are called parabolic weights, which satisfies this following sequence. So we are assigning this alpha IP to each subspace PP, I. And we say that the alpha is full flag, mean that this sequence is full flag if dimension of each subsequent quotient is equal to 1. So what does it mean? That for any rank R vector bundle, there are exactly R many subspaces. Okay, here. So this is for all points over D. So this is called full flag. So we will consider the full flag throughout this talk. Okay. And also there is notion of parabolic degree. So parabolic degree is degree of the underlying bundle plus some additional part. Okay, similarly, we have the definition parabolic Higgs bundle is a parabolic bundle together with the Higgs field from T to E tensor KD. So KD means K tensor OD. Okay. So this on extra condition is that the Higgs field is strongly parabolic. What does it mean? So it means that this phi restricted to P. Okay. So this sends EP, I to the next one, EP, I plus 1. Okay. So in other words, this Higgs field phi is nilpotent over each point of T. So strongly parabolic means nilpotent over D, the Higgs field, and therefore the trace of phi power I, they vanishes at each point D. Okay. And suppose this is moduli space of stable parabolic Higgs bundles with type type alpha and fixed rank, fixed degree. And then we have the parabolic person of the Hitchin map. Okay. So it sends again map. I mean, the definition is the same, but only the difference is that the Higgs and the Hitchin base, that is the vector space here, it is different from the previous one. But the definition is same. It sends the Higgs field to the coefficients of its characteristic polynomial. Okay, now in the main object of our talk. So it's a symplectic parabolic Higgs bundle. Okay. So let tau is a bilinear form from E star tensor E star to OX. OX is a trivial line bundle over X. Okay. You can replace this OX by any other line bundle, but for simplicity, you can assume that the tau takes values in the trivial line bundle. So this is bilinear form. Okay. So a symplectic parabolic bundle means this is a parabolic bundle together with this non-degenerate skew symmetric tau. And symplectic parabolic Higgs bundle means, so that is a symplectic parabolic bundle, and there is a Higgs field which is compatible with tau and with the parabolic structure. Okay. So this compatibility condition here induces a nice property on the, because the compatibility condition of the Higgs field, the characteristic polynomial of phi has a nice form. So this is of this form. The characteristic polynomial of phi is basically, so there are no odd coefficients here. So all exponents are even. Okay. So 2m, 2m minus 2 to 0. So these coefficients h2i, they are sections of k power 2i d 2i minus 1. Okay. And again, if you consider the zeros of this characteristic polynomial, you will get the spectral curve, which is S. And since there are no odd coefficients, the spectral curve, it has an involution, sigma lambda equal to minus lambda. Okay, because there are no odd coefficients here. And together with that, we have a double cover, which is a morphism from S to S mod sigma. This is unramified cover. Okay. And if you consider with these, we have a prime variety, which is for this morphism, a prime variety, which is subset of the Jacobian. Okay, so for which sigma star L is isomorphic to L dual, all those line bundles. Okay, so since prime variety is a subset of Jacobian, so it is also abelian variety. Okay, so and the result is for this we have the Hitchin map, and the genetic fiber of that Hitchin map, they're isomorphic to this prime variety. So in general, all those genetic fibers of the Hitchin map for each cases, they are all abelian varieties of some form. Sometimes it's Jacobian or a open subset of the Jacobian, but it's abelian variety. That's all we need to prove the next theorems. Okay. So let me come to the second part, which is Torelli theorems. So the basic Torelli theorem says, so consider two compact Riemann surfaces of the same genus, greater than or equal to 2. The classic Torelli theorem says, if the Jacobian are isomorphic as a polarized variety, Jacobian means all degree 0 line bundles. Okay, if they are isomorphic, then the curves are isomorphic. Okay? So you can recover the curve from the Jacobians itself. So this is abelian setup because Jacobian is an abelian variety. So what is the non-abelian analog? Okay, so we have to replace the Jacobian by moduli spaces. There is the moduli spaces over X, moduli spaces of vector bundles, moduli spaces of parabolic bundles, and so on. So for moduli spaces of parabolic vector bundle, Mumford and Newstead prove for rank 2 case prove this Torelli theorem. That is, if the moduli space of vector bundles are isomorphic, then the underlying curves are isomorphic. And later, Narasimhan and Ramanan, prove the general version for any rank, consider any rank. Then we have the Torelli theorem. Then for parabolic bundles, Balaji, Banu, and Biswas proved a Torelli theorem for the rank 2 case. And recently, Alfaya and Gomez proved the same thing for any rank, assuming genus greater than equal to 4. That is also our assumption. In our case also, we will assume that genus greater than equal to 4. We also have Torelli theorem for principal bundles, which was proved by Biswas and Hoffman. And for parabolic Higgs bundle, the Gomez and Logares proved a Torelli theorem, okay, for rank 2 case. And together with this theorem, the Alfaya and Gomez, if you assume that result, then this parabolic Higgs bundle case also, for any rank, this is done. Okay. Okay. So for Torelli for symplectic parabolic vector bundles. So let this is as denoted by moduli space of symplectic parabolic bundles. Okay. And so these are all the assumptions that our weights, the parabolic weights, they are small and they are rational. And we also assume that the rank and degree are co-prime. Okay. The statement is, if we have two different compact Riemann surfaces, X and X prime, together with a finite set D and D prime, and assuming genus greater than equal to 4, then the result is that if these two moduli spaces over X and X prime, there is a moduli space of symplectic parabolic, stable symplectic parabolic bundles. Then we have a isomorphism from X to X prime, which sends that set D to D prime. So let me steps of the proof. Okay, so consider the Hitchin discriminant, which is the locus of singular spectral curves. Okay, so the spectral curves, some are singular, some non-singular. For a genetic point, the spectral curve is non-singular, but there are some singular spectral curves too. So consider those spectral curves, call it D. Then consider the intersection with the last coefficients of the vector space A, which is the base of the Hitchin map, the last coefficient, that A to M. Consider the intersection with that, then it has several irreducible components, okay. Cx, and for each parabolic point we have one irreducible components for each parabolic points, and this was general one, C capital X, and these are C small x. Okay. Capital X is for the curve and small x are the points inside D. And the thing is that the projectivization of this Cx, this component, is a dual of the curve X, and the projectivization of this C small x is a dual of small x. Okay. And the Hitchin discriminant here, this locus of the singular spectral curves, that can be defined uniquely. That's the main part. Okay, so if we have a moduli space, then we have the Hitchin discriminant, which is an unique locus, and then from there we have this we can recover the curve X and those points, all those parabolic points. This is the main idea of the proof. Okay, so yeah, and finally, so the moduli space, I consider the moduli space of stable symplectic parabolic Higgs bundles. We will prove this result with using the last one. Okay, so without Higgs one, we will use that result to prove this Torelli theorem. So if we have an isomorphism of this kind, okay, then we have the isomorphism between the curves. So it's basically the same. So there is an isomorphism X between X and X prime, sending let's say D to D prime. Okay. Steps of the proof. Okay. So H inverse 0. H inverse 0 means H is the Hitchin map, and H inverse 0 means those characteristic polynomial whose all coefficients are 0. Okay. So that is exactly of the form x power r, which is nilpotent one. So that is why this name. So it's called the nilpotent cone, because this fiber H inverse 0, those the Higgs field here have all the coefficients of the characteristic polynomial. They are all 0. Okay. And this is kind of most singular fiber. Okay. So this is extremely important fiber and kind of most singular. This is absolutely not non-singular fiber. Okay. So and it has several reducible components. This fiber H inverse 0. It's called the nilpotent cone. Okay. And the moduli space of stable symplectic parabolic bundles, that is without the Higgs field, that sits inside this fiber H inverse 0. Okay, because our in mx the Higgs field, that is 0, so characteristic polynomial is also 0, so that sits inside the nilpotent cone H inverse 0. Not only that, in fact, this moduli space sits inside uniquely as an irreducible component that does not admit a non-trivial sister action. So we have already seen that the moduli space of Higgs bundles, it has a sister action. Okay? And this moduli space without the Higgs one, that does not admit a non-trivial sister action. So there is, it sits uniquely. So if you have the moduli space of stable symplectic parabolic Higgs bundle, then if you consider the nilpotent cone, and then the moduli space of stable symplectic parabolic bundles without Higgs, that sits inside uniquely. So you can recover, so from this moduli space, you can recover this one, and by the previous result, okay, so we can recover the curve. So if you have an isomorphism in the Higgs level, then you have an isomorphism in the non-Higgs level, and then by the last theorem, you have the isomorphism between x and x prime. Okay. So only thing is that we do not have the so when we have the isomorphism here, it is an abstract variety. This isomorphism as an abstract variety. So you don't know about the Hitchin map in that case. So which can be recovered from this isomorphism, the Hitchin map can be recovered. Once that is done, then consider the nilpotent cone and then the non-Higgs moduli space that sits inside that uniquely. Okay, I guess I'm done. Okay, I'm done. Any questions? Something?
So let us thanks to the speaker. Any question in the seminar hall? Like there is no question from the seminar hall, maybe we can ask the sole participant question. Like there is no other question, so let us thanks to the speaker once again. Oh, 5.